This video has been supported by Skillshare. Hey guys, I received such a suspicious package from YouTube that it startled some German officials out of their third lunch break. I couldn't agree more, its sudden arrival startled me too. Normally such an inspection takes a long time, and then you've got to go pick it up personally at the most inconvenient location possible. Well, seems like the customs people were unable to cause more problems this time, and they had to grudgingly send it on its way. But luckily there's more customs. Custom demands that packages like these be opened in the most impractical way possible. No worries, the spindle has air purge, and the linear rails and ball screws have wipers to keep the dust out. But I'm still looking desperately for some telescopic way covers. If you've got some, let me know. Okay, we are almost ready for the Cnc season finale, with the first productive chips and the first micrometer results. But before jumping to that conclusion, there is one more very important element I want to have in the series. The motion control system. Most 3D printers accept G-code directly. You can give them a couple of commands and their poor little microcontroller has to turn them into tens of thousands of precisely timed step direction pulses to move the motors synchronously, while also translating future instructions, running multiple PID loops, and reporting progress over network or a display or whatever. And you don't even need a degree to operate them, usually. The motion controller hides all of the extremely complicated internals to give you control over millimeters instead of registers and step pulses. It's not doing such a terrific job though. I've programmed a perfectly uniform extruder movement, and I'm triggering the oscilloscope every 16 kilo clock pulses. Ideally, the step pulses should always occur at regular, predictable times, with respect to real outside world time. But the Tektronix histogram display shows that they are jittery AF, because the controller has to work dozens of jobs on the side. The Cetus controller makes that work by avoiding jitter with respect to the step pulses of the other axes. So all the movements are synchronous, but not necessarily uniform in real time. That's a solution only for lightweight machines. You can probably tell where I'm going with this. In conclusion, planning, timing, and hardware abstraction are kind of the most important aspects of a 3D printing motion controller. Coincidentally, it's exactly the same points for my CNC machine. And somehow for most of my YouTube videos as well, isn't it? This is my Cnc Control Panel. It's a work in progress, so no freaking out please. Hey, what did I just say? It's not that... It's pretty bad, isn't it? I'll work on it some more. It takes a bit of a bigger microcontroller to handle all of this stuff. I would recommend the most normal, few years old office PC. This was an HP Compaq 8200 Elite. I removed everything I didn't need and then some. I had to put that back in because the BIOS settings are very important. I went through all of them and disabled the ones that sounded like they would make decisions on their own. Like smart boost, automatic power saving, surprise reboot. I just kicked everything out that didn't sound necessary. That way the machine can focus on its 3 aforementioned tasks, and not cater to the needs of an Intel management engine or think about power states. LinuxCNC is now better than ever with a very compatible real-time kernel mod. I had none of the old hardware compatibility issues. Maybe because no hardware is left in my PC, but even the high-tech pre-compiled TeamViewer installable worked right out of the box. Fantastic. As soon as I trust my machine enough, I can let it do longer jobs on its own and monitor progress from my living room. But how well are we actually doing in the real-time department now? LinuxCNC has tools built in to measure jitter. These are deviations from the configured thread times. The numbers get worse when you do stuff in the background. and it's important to know about them and to be prepared for the possibility of such delays. But this would still be a very good result, easily sufficient for generating a lot of step direction pulses in software. That's precisely what I did with all my CNC machines until now. But this monster turned out to be a little bit more everything. It needs way more GPIO pins than an old parallel port or two could deliver. The servo drives in particular can be configured for absurdly high resolutions, both in the positioning and the encoder feedback. And in spite of good results in the latency test, I don't want things to depend on the whims of an operating system. I mean, it's a nice and pure Debian. It won't ask you about a reboot for software updates, only to ignore your answer and reboot half an hour later when nobody's looking. But I've been mentioning FPGA motion controllers in a couple of videos now, in anticipation of finally using this. That's a Mesa 6i24 FPGA card, and it's LinuxCNC's best buddy. Tools for reading and writing firmware and configuration are built right in. And there's even a graphical wizard to get you started with a generic configuration. I understand the appeal. These cards solve all the timing and interfacing problems by just being chunks of freely configurable hardware with tons of GPIO pins and an operating system independent clock. As long as you're not plugging them into your own sketchy PCI Express extensions, they probably won't even lock up from oil pump EMI. Oh, don't pay attention to the 10 layers of aluminium tape everywhere. That's nothing special. But I also understand why starting with LinuxCNC and a Mesa card might look a bit intimidating at first. But it's really not. You've got to flash one of the pre-made bit files. Usually that will have more hardware than you need, like 8 step generators, 4 PWM generators, 4 encoder counters and so forth. Of course you don't have to use all of those step gens, and more importantly, the pins associated to the leftovers can just be used as normal GPIOs instead. Thanks to a couple of Bavarian pandas and squirrels, I don't think many of the 72 GPIOs will be left unused in the end. Nice. The servo drives on their own demand a lot of pins, and even some shielded twisted pair cable, for the sensitive high-frequency positioning and feedback signals. The LinuxCNC configuration wizard doesn't fully support the infinite number of combinations that are possible with Mesa cards and daughter boards. So you've got to let it create something close and then do the rest manually in the hell file. This is, again, much more simple than it looks. You just have to connect pins and signals. There aren't even any loops, conditional statements, or segmentation faults like in a proper programming language. Most numeric values, like max velocity and max acceleration, are references to the ini file, so that you can do fine-tuning in a more neatly arranged file once the hardware abstraction layer is complete. It's very specific, so it won't be very helpful to most, but I'll upload and link my entire machine configuration below. Right after some even more specific PID tuning. Generally, when transitioning from a simple old open-loop stepper system to high-resolution encoder feedback, you're probably going to be something between disappointed and horrified. Because what used to be nice and effortlessly round numbers is now an oscillating RNG. The truth, however, is that with steppers it probably looked even worse. There was just no encoder to tell you about it. Now the point of PID tuning is to find the perfect compromise between speed and accuracy. To accomplish that, we are using two more wonderful LinuxCNC tools. The oscilloscope and this live tuning tool that allows us to change parameters without restarting everything. The primary goal is to get a parameter called axis F error as close as possible to 0, because then the axis is exactly where the motion controller wants it. When that's the case for all 3 axes at all times, we'll reach perfection and finally be ready to show off some micrometer results. If everything has been configured correctly before, these settings and the oscilloscope readings are in machine units. Millimeters for me. That makes the whole thing a bit less abstract and a bit easier to talk about. The proportional term P is kind of the workhorse. The error value is multiplied by p, so the further away the axis is from the set point, the higher is the PID controller's output. Within the reasonable limit set further down, of course, otherwise the heavy clamping plate could be propelled to absolutely destructive low-orbit escape velocities. Okay, no thanks. The I term is related to how long an error has been occurring, and we don't use that. Our errors can't be occurring for too long anyway, otherwise something else would be seriously wrong. The derivative term looks at how fast an error is changing, and we might have to use that to dampen some oscillations if we can't get rid of them otherwise. The feed-forward terms add zero-order, first-order and second-order derivatives of the commanded value. So with FF1 you can add something related to speed, and with FF2 you can add something related to acceleration. By manipulating these numbers and looking at what they are doing to the waveform, I'm slowly inching forward in the right direction. I mean millimetering, of course. We are certainly not inching over here. But that'll all change again once I start introducing chaos with machining different mass workpieces and stuff. So I'm not really aiming for perfection in a dry run. Perfection has not looked this achievable before though. I'll introduce you to this beautiful spindle in the grand finale next, once the red carpet has been rolled out for it and the oil pipelines have been organized and hidden. For this one I've got one or two last LinuxCNC interface tricks. The servo kit came with this USB dongle for configuring the drives via RS485 Modbus. I've connected the 3 servo drives as well as the spindle VFD to one common Modbus. Every participant has a configurable address. That way I can read and write parameters from and to every device. Someone has to write a hell component, something like a library, to make the servo drives more accessible. But for the spindle VFD that exists already. Here's how I got that working with the USB dongle. Oh wait, that didn't work. These are the instructions. Now I can read, for example, motor current, a variable that's very proportional to motor load. I think that's a very interesting number to keep an eye on, to be able to judge how far you're pushing your spindle at any given moment. Here's something else to keep an eye on. Skillshare. It's an online learning community for creators with more than 25,000 classes in design, business and more. Their premium membership gives you unlimited access so you can join the classes and communities that are just right for you. Whether you want to fuel your curiosity, creativity or even career, Skillshare is the perfect place to keep you learning and thriving. There's even an entire 90-minute class about PID controllers, their mathematics, programming and simulation. After digesting such a formal introduction, my tuning felt much less like turning random knobs and looking what comes out. Skillshare is also super affordable with an annual subscription for less than $10 a month. Join more than 7 million creators who are already learning with Skillshare. Click the link below for 2 months free trial. And thank you for watching. See you next time.